Welcome to our presentation. My name is Haoshang Wang. I am from Tsinghua University. The paper I will present today is Optimal Green Certificate Auction Design Embedding Economic Dispatch. This work is advised by Professor Chunye Wu in the Chinese University of Hong Kong, Shenzhen.
Global warming is coming. The Paris Agreement calls for greater worldwide efforts to combat global warming by reducing carbon emissions. To achieve this goal, carbon tax and cap and trade programs are ready by policymakers. However, carbon tax and cap and trade programs often make the regions in a non-favorable position in the global economy. More importantly, the public often challenges the actual usage of the extra payment collected from these carbon-related policies. They often design the programs without incentive for generating companies and also the consideration of the generation process. On the other hand, carbon reduction needs a massive investment to support carbon capture technology's rapid development and also its commercialization and industrialization. We propose a potential solution to align the interests between the public and the policymakers, that is to invest the extra payment in carbon capture technologies. It can be achieved by a well-designed green certificate auction. The auction needs to be revenue maximization for the auctioneer for the following better investment. The auctioneer can be the system operator in the power grid. They can better consider the economic dispatch, (ED), in generating process and also the willingness of generating companies through the auction. Next we show some related work for our auction design. For the carbon market, there are several pieces of literature about carbon rights or green certificates. According to the form of goods, we can divide the works into one-piece auctions and multi-piece auctions. The one-piece auction means selling the certificates one by one. Some auctions like classical sealed auction, then sequential ascending auction and ascending clock auction are considered recently. But it is difficult to derive the truthfulness and optimality characteristics of such auctions. Then for multiple goods, some auctions like double auction and multi-unit auction in the Bayesian framework are proposed. However, they seldomly consider involving rigorous modeling of the whole dispatch process. For the other stream of related works, we focus on the homogeneous divisible good auction. One traditional method is to discretize it to multiple goods and conduct the approximate single items auction, but it is difficult to derive the theoretical guarantee. Then, the continuous modeling of goods, which is pioneered by Wilson et al., has provided us more insights. Our work is based on the framework of Maskin et al. Works at 2000. And Liu et al. Also propose a good approximate algorithm for this type of auction. Then for the homogeneous divisible good auction, we also consider willingness distribution analysis, which measures the ability of our auction when we do not know the willingness of participants. One common analysis is sample complexity analysis, which is proposed by Cole and Roughgarden for the single item auction and nonlinear pricing. But the kind of analysis has still not been extended to the homogeneous divisible good auctions. We can specify the challenges and contributions in detail. Our auction design needs to consider the generating process, that is another optimization problem ED process and also the auction process. We need to achieve the optimality of the results after two processes, which is a multi-objective optimization. Then we also conduct sample complexity analysis in the multi-demand auction when the willingness of participants cannot be well identified, which has never been studied, especially with ED coupling. Therefore, our contributions can be summarized as follows. We study the interdependency between the green certificate auction and the ED process and propose a new concept, the virtual demand, to decouple the interdependency. We design an optimal, truthful and individually rational auction and also extend it to several scenarios. We construct an upper bound for the number of samples needed to estimate the value of bidders accurately. This bound informs us when the auction design can achieve guaranteed performances. We first provide some notations about our auction. First, our divisible green certificates is limited. The total amount is Q. Then we denote the total number of bidders, which is also generators, as N. We also assume that the type for the auction for the generator I, which describes the willingness of the generator for the certificate, is bounded and denoted by VI. Auction outcome can be described by the tuple allocation Qi and payment Pi. We provide a uniform demand price function RQi. VI to describe the utility of the bidders with respect to the type and allocation. We assume R is uniform and decrease with Qi, increase with Vi. We also assume the elasticity of R is non-decreasing and R is concave in VI. Then the actual utility described by valuation function with auction outcome Qi and Vi as psi I, and it is related to Ri as a integration form. Then we also assume Vi as a random variable with cumulative probability function, CDF, big FIV, and probability density function, PDF, small FIV, with a bounded support. We also assume Vi is regular, which means this term is increasing. Then we turn to the ED's formulation. We consider a simplified ED modeling. We assume the generator I has a linear cost function with coefficient alpha I and also has green generation capacity Bi, which means the maximal generation if the generator does not buy any certificate. We assume the demand D can be satisfied by the Bi and the total certificate Q. We construct problem P1 as our ED process. The system operator needs to minimize total system costs with the meet of the demand. We also set the prices for the ED process as lambda. Then we denote the change of the generator as delta G. We denote the price with the auction as lambda and without auction as lambda 0. Then delta G can be expressed as this form. When the marginal cost is lower than the price with the auction, the change of generator is Qi. Then if it participates the ED without auction but not participate with the auction, the generation change should be decided as Bi, and if it does not participate the ED with the auction, it will not participate with the auction, since the auction will provide more supply of generation and the change is 0. When the marginal cost is lower than the price with auction, the generation change is, then we can derive the extra profit for generator I with or without auction as Vi. It can be described as two parts as the figures show. The white box means the original revenue and the whole box means the total revenue. The blue term is related to the blue box and so is the green term. They reflect the extra revenue from extra generation and the deficit from the price down. Then it can be taken part into a form with Gi and without Gi as follows. We give the objective for both the auction participants and the auctioneer. For the generators, the utility function can be described as Ui. It consists of the valuation of the green certificate, the payment and the extra profit in the ED process as we stated before. We also introduce a new notion of expected surplus. It shows the expected utility if the generator bids X with type Vi. I means all other generators except for I. Then we also propose the objective for the auctioneer to be the expectation of all revenue in the auction and all extra payment in the ED process, which can be described as the extra profit plus the cost, and the cost is not needed to be afforded by the system operator. Here we ignore some constant terms which will not influence our optimization problem. The optimization reflects the optimality of our proposed mechanism. We also need to guarantee the truthfulness and rationality of our proposed auction. We propose Bayesian incentive compatibility (BIC) criteria with expected surplus as follows, which shows that the truthful bidding is the best bidding. And we also construct interim individual rationality (interim IR) conditions, which means the expected surplus is larger than 0. We need to propose a mechanism to achieve the objective subject to BIC and interim IR. Then to design our mechanism, we need to first transfer the BIC and IR constraints to clearer conditions. Then we provide our lemma 1, which gives an equivalent condition for the BIC and IR constraints. The lemma shows that if our allocation rule is monotonic, that is Qi is non-decreasing with Vi, the BIC and interim IR condition is necessary and sufficient for the following condition, which combines the expected surplus and an integration form for valuation function psi. This lemma actually can be intuitive. We first know the definition of expected surplus as this form. Then BIC can be transferred to the following conditions that X is argument of this constructed function, since pi I, Vi is always the maximal for pi I xi Vi. Then we take the derivative for the function and let it be 0 at point X. We will derive pi I, Vi's derivative through the calculation of pi I xi Vi's partial derivative. We can integrate it to derive the lemma and embed the simple fact that with no expected surplus the bidder will not take part in the auction to satisfy interim IR. Therefore, we derive an equivalent condition for BIC and interim IR. Then with the conditions, we can focus on our optimization problem and give the payment and allocation design for auction. Without loss of generality, we set the expected surplus of the lowest value as 0. Then we can derive the BIC equivalence as this. Then we can derive the payment should be as this formulation. Then we take it back to the objective and derive that the objective can be transferred to this function summation. It helps us to propose our allocation rules. We need to optimize the function as P2, with Qi's allocation to achieve optimality. Here, we propose our notion of virtual demand function as the form in the blue box for fixed lambda. We actually need to calculate each lambda for generators and optimize the summation with the constraints of limited supply. Here, we set the Lagrange multiplier as μ for this supply constraint. Then for the payment, we can simply design as before to satisfy the BIC conditions. Then we can also write down the KKT conditions for optimal Qi with the shadow price μ. The optimization will try to make all generators' margin virtual demand functions equal to the μ. If it cannot be satisfied for some generator, no allocation will be assigned to it. Note that we mark the lambda as blue in the last page. That means we need to consider different lambdas to derive different virtual demand functions. Thanks to the linear constraints, the lambda can only come from the margin cost of each generator. Then we can conduct the auction for all possible lambdas and choose the best with linear time complexity. Then we also guarantee that there always exists lambda that satisfies the demand D in our auction. It is intuitive since demand is lower than supply. The final step is to show the monotonicity to support the BIC equivalence. We show it as proposition 1. It also shows the interesting fact that VI's increasing will drive ED price closer to alpha I, which shows the impact of the auction to the ED market. Then we also try to extend our auction to more realistic scenes. We first consider the physical capacity constraints. We denote the maximal physical generation capacity as Gi. We know that Qi plus Bi should be smaller than Gi. Then we divide it into the non-competitive scenes and competitive scenes. In non-competitive scenes, all the generators are limited by the physical generation and can receive all the certificates. They are not in the competition for the certificates and the allocation should be the maximal certificate that they can receive. Then the payment also follows the BIC equivalence. Then for the competitive scenes, we need to add the physical generation constraints into an auction optimization as problem, P3. Then after solving the problem, P3, we can derive payment as before. Next, we also discuss about the extension for nonlinear cases with transmission constraints. It can be complex and here we only propose a formal description but not try to specify it and solve the problem. We denote C as the optimal solution for the ED process given all Qi s. Lambda I asterisk is the payment for the ED process. Gi is the generation. Then we can derive the Qi determined by problem, P4, which can be derived by the definition of the auction and our BIC conditions. Then capacity constraints and transmissions constraints should also be included in P4. Then the payment can be designed by the BIC equivalence and extra profit to achieve the truthfulness. To be closer to the reality, we also consider the scenes that the distribution of VI is unknown. In this scenario, we need to learn the VI's distribution from the historical samples. The problem should be how many samples or how many rounds we need to derive an optimal solution, which introduce the problem of sample complexity analysis. With the introduction in Cole et al., the analysis hopes an input of the historical T-sample profiles the vector v⁻j for j in 1 to t. Each v⁻j have all VI samples at that time. What we should do is to construct an approximation auction utilizing the historical samples. Then the auction takes the next turn's value, which is drawn from the unknown original distribution as an input, and we hope to show the high probability bound for the approximate error between the approximation auction A and optimal auction for the unknown distribution with sample number t. Then we try to specify the statement before. We assume the samples are from the unknown distribution F. The empirical distribution derived from samples as E. We also denote the auction mechanism H as a map from distribution to revenue. Then we give the specific expression of the sample complexity. The sample complexity S, epsilon, delta, means the minimum number of samples for any distribution F. We can find a mechanism H with probability 1 minus delta satisfying the approximate error is less than epsilon. Then we provide our theorem 4. It shows that in our proposed green certificate auction with n generators, the sample complexity is upper bound by this magnitude. To show the theorem, we can construct an auxiliary mechanism for the discrete distribution with several intervals and round the original and empirical distribution to it. It bridges the original distribution and empirical distribution, and we can show the errors for auxiliary mechanism and optimal mechanism for both original distribution and empirical distribution are small to complete the proof. Finally, we conduct the numerical studies to verify our auction with EIA dataset for USA power plants in 2019. We first verify the optimality of our mechanism, compared with an auction without ED and random assignment. We can find out that the auction without ED will lose more revenue since the allocation's influences are not considered. Then for the random assignment, it is obvious that it will not achieve optimality. Then we verify the truthfulness by changing the bid of the bidder with a fixed type value. Then we can find out that it will earn the most when bidding truthfully, otherwise will suffer a decrease in the utility. It fully shows the truthfulness of our mechanism. We also conduct empirical studies to extend our mechanism to multi-shot. Our proposed auction above can be used in the one-shot scene. However, in multiple shots, the certificate will accumulate and influence the incentive of participants. The effects should be considered. Then in this part, we try to extend our auction into multi-shot with numerical studies. Here, to simplify the problem, we assume that value is only bid at first. The system operator needs to determine the total certificate quantity in each period and then conduct auction-embedded ED with that amount of certificates. Then to prevent the certificate excessive release, we consider releasing cost for the certificate. The specific process can be described as an online learning problem as the figure shows. The input for the system operator is the demand at the current time dt, historical release amount Q0 to Qt1 and the current remaining certificate for each participant and the historical demand. The action of the system operator is to determine the current time total amount and get the feedback reward as the payment of the participants. The total objective is to maximize the revenue for all periods minus the total release cost. Then we solve this online learning problem by some heuristic strategies. We choose the fixed release random release, the proportional to last mean demand release, and RL release for the problem. From the results, we can find out that RL shows the best performance in the revenue. Figure B shows that the release of the certificates often increases when the demand in the following period increases for the RL. It shows that RL tends to store more spare certificates when demand is slightly increasing. Finally, we observe the tendency of the amount for the certificates that are still unused for a particular player in figure C. Most of time, when the players take part in the dispatch, the certificate could be used for generation. However, there could be late nights when the demand decreases sharply, leading to many unused certificates. It again emphasizes the importance of reducing these excess useless certificates which could influence the incentive of the next period's auction. Figure C also shows that our RL strategy successfully decreases the amount of excess certificates. From the studies, we know RL is effective to learn a good strategy from the experiences. And in practice implementation, more detailed strategies can also be considered. Finally, we verify our proposed theoretically bound for the sample complexity. We choose two common distributions, uniform distribution and normal distribution with unknown parameters as our types distribution. Then we construct an auction based on the proof of our theorem 4 with samples and show the approximate error and error probability with sample increasing. We can find out that the error decreases sharply as the sample size increases, and we can find our upper bound works well for the approximate error. Next, we study the impact of error probability delta, which is the probability that we could not derive a good approximate auction considering the sample number and error requirement epsilon. It is obvious that, the more the number of samples increases, the more the error probability decreases. And also the error probability increases by improving the error requirements. We can find our bounds still work but looser for the normal distribution than uniform distribution. That is because we need to afford more if we misjudge the hazard rate for normal distribution in our theoretical analysis, and our auction would also calculate a less accurate virtual demand compared with the uniform distribution. This work can be extended in many ways. More tighter sample complexity bounds can be calculated and more kinds of value functions that do not satisfy our assumptions can be considered. And also the analysis based on a more detailed ED formulation can also be conducted. That's all for my presentation. Thanks.